Okay, so this particular lab is of Ferranti effect of in a transmission line. Okay, we'll see for a Ferranti effect in a transmission line. I would be using your MATLAB, okay, Simulink and your Simulink part, and as well as your coding to represent these two, okay, to observe how uh, your presentations, okay, how you could draw and how you could do so. Okay, so I have taken this particular segment, okay, where Ferranti effect is being shown. Okay, this is a lab manual, okay, which we do in hardware. So do not worry about the equipment's ratings could be different for different cases. Okay, there are cases has been doing in hardware. Okay, I wanted to show you you all in virtual lab as well, but it's not working right now. Virtual lab has not been responding, so we'll do in this particular segment. Okay, so let's begin. So the aim of this experiment is to observe the Ferranti effect in model of transmission line. Okay, so first we'll see the what is Ferranti effect. In general terms, if I will explain, okay, when there is no load condition, okay, the sending end voltage will be lower than the receiving end voltage. That is called the current effect, or you could say in the other words, the receiving end voltage increases. Okay, when there is a no load condition. Okay, or uh, in if we go the opposite side, okay, for the longer when it is loaded for the longer transmission line, this effect has been seen. Okay, so we'll see over here what has been written. Okay, long transmission line of cables draw a substantial quantity of charge current. Okay, if such line or cable is open circuited or very lightly loaded at receiving end, okay, the voltage at receiving end may become greater than the voltage in the sending end, okay, due to capacitive reactance. Okay, this is the reason, and this is what the effect is also known about. Okay, this is known as Ferranti effect. Both capacitance and inductance is responsible to produce this effect. Okay, now the capacitance, which is responsible for charging current, is negligible in short line, but significantly in medium line and appreciable in the long line. Okay, we generally okay, this capacitance, this is responsible for the charging current, is absent in short line. We do not neglect. So what we'll do, we'll draw this segment only. Okay, in short circuit, a small short transmission line, we'll see the effect. It is there in now. Hence, this phenomena occurs in medium and long lines. Okay, as the absence of capacitance in short medium time, they do not occur in that, but in medium and long run, this occur. Okay, the figure what is being shown in there, okay, represent the transmission line of a equipment, or that is being the pi model. Okay, the voltage rise is proportional to the square of length of line length. Okay, see this. We'll study on this is a pi network. So we in college we have a model. Okay, we have a model, transmission model, or we could see that effect in that particular model. Okay, now in general practice, we know for all the electrical system, current flows from the region of higher potential to the region of lower potential to compensate the to compensate for the electrical potential difference that exists in the system. Okay. Now, in practical cases, the sending end voltage is higher than the receiving end voltage. Generally, it happens. Okay, the sending what we are sending, okay, and what they are receiving would be very high, will be different, and the sending will be different because of the losses. Okay, there will be the transmission loss, the heating loss, okay, IR square loss, whatever you say, that losses occur in that end. Okay, so the current flows from the source or the supply to the load. Okay, but the person who got this effect, okay, the Sir SZ Ferranti, okay, in year 1890, okay, came up with an astonishing theory about medium and long transmission line, suggesting that in case of light loading or no load operation, the transmission system, okay, the receiving end voltage often increases beyond the sending end voltages, okay, leading to a phenomenon known as Ferranti effect in power system. So in he Sir as said Ferranti, okay, found out this. They brought this theory that in light load condition and no load condition in medium and long transmission line, this voltage increases, receiving voltage increases than the sending end voltage. Okay, so a long transmission line can be considered to compose a considerably high amount of capacitance and inductor, okay, distributed across the entire length of the line. Okay, fertility effect occurs when current drawn by the distributed capacitance of a line itself is greater than the current associated with the load at the receiving end of the line. Okay, during light load, or generally we will consider about light load and no load conditions only. Okay, now the capacitor charging current leads to voltage drop across a line inductor of a transmission system, which in phase with the sending end voltage. Okay, voltages, the voltage drop keeps on increasing additively as we move towards the load end of the line, and subsequently the receiving end voltage tends to get a larger than applied voltage. Okay, the applied voltage leading to the phenomena that is called fraternity effect. Okay, now so this is the reason, okay, why it happens. Okay, you could account, okay, this capacitor charging current leads to voltage drop across the line, okay, inductor of a transmission system, okay, which is in phase with the sending end voltages. Now this voltage drop keeps on increasing. Okay, this voltage drop keeps on increasing additively as we move towards the load end, okay, of the line, and subsequently the receiving end voltage tends to get larger than the applied voltage, leading to the phenomenon called this potential. We'll see this thing in this is the diagram. Okay, we 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 have the model in our lab. We'll see. We'll not go through this particular uh, thing because you're not doing hardware. We'll be focusing on MATLAB and your yeah, MATLAB Simulink and coding. Okay, so both will be there. The coding would be also there, and Simulink part would be also be there in the same thing. So these are the positive. If you go through, will not go. Okay, we'll see the ratings. Okay, and we'll return to the this question. These are the very necessary thing whenever you are doing lab. So you are able to answer, okay, these questions when we are completed to the lab. Okay, so the our lab function will be based on this. Okay, what first of all is what is the fertility effect? That is obvious, you could understand. Okay, and the second is how to reduce fertility effect in transmission line is also you have to seek of. Okay, you could also seek of, right? Now third is why a fertility effect occur in a transmission line. Okay, this also you have to see. Okay, we have just discussed this. Okay, what happens during the Ferranti effect? This also you will be able to know. So before getting to the experiment, I could say on the based on the explanation, you could answer these 4 questions. Okay, but now post viva questions. Okay, a transmission line of 200 kilometers is supplying a 50 hertz frequency. What is the percentage rise in the voltage at the receiving end? This we have to seek. Okay, after what this your viva part is the lab you will be done, you have to know this. Okay, when does the Ferranti effect happen on transmission line? Okay, this also you have to very clear. Okay, and when is the Ferranti effect on long transmission line is experienced? Okay, so these are the questions you have to answer as we end with this. Okay, so let's go to the MATLAB and let's start. Okay, this is MATLAB. Let's go to your Simulink part. We'll save this as okay. So what we'll do, we'll create a system. Okay, we'll create a system in this, and accordingly we will be performing it values and right now. What you need, first of all, what you need, I need a source. Okay, so we'll type over here 3-phase source. Okay, so there will be a 3-phase source. Yeah, this is your 3-phase source. Okay, we'll name this as a 3-phase source. Now you require now is a measurement unit, right? So we'll type over here 3-phase VI. Okay, that is VI measurement. Okay, we'll type this. Okay, now so what we are actually measuring in this, we are totally focusing on only one factor, that is your V. So we could edit this part. Okay, V required no. Okay, we required only, that is your VI measurement thing, and that is your, and we will be measuring your face to face. Okay, only voltage measurement, no current measurement, because we have to see only Vs and that's it. Okay, so we will, okay, so what is next, what you need, Next is you required a line. Okay, so we could get you could find from this segment also. Okay, 3 phase PI section line. I think so it will be there. Yeah, it is there, right? It is there. You could consider this. Now you could connect. Okay, this is your line. Now further we have to connect this particular thing to again. Okay, this is your transmission line, entire transmission line. So what we have to find again, that is your this measurement unit. So we'll copy and we'll paste over here, and it gets connected. Let's connect it. Okay, it is connected. So we'll change of name. Measurement would be your sending end. We'll write over here receiving end. Okay, so this is your display part, this is your segment, and this is your segment. Right now what you need to connect, you need to connect the measurement unit. Okay, so we need RMS. Okay, we need RMS. No, not this part. Yeah, this RMS, and we also need display. Okay, same for this. You need to copy, paste this display, copy, paste. Okay, so this will be showing you VS, and this would be saying you VR. Okay, this is the entire thing. Okay, now let's give the value to it. Okay, let's give the value to it. Let's open this a three-phase system. Okay, so we'll keep this as a parameter, as a configuration. Okay, YG format. Okay, we'll change this value. We'll give not 25. We'll give, let's give 110. Okay, let's give this as a 50. Okay, and let the rest all be as it is. Okay, now we put degrees over here, and okay, face to face, no. Okay, fine, this is okay. Each one, okay, this, okay. Now this is what we have to fill. Okay, we'll take over this. Now first of all, we have to change this. We have taken frequency as 50, so it will be your 50. Now next we'll give this positive 0 sequence resistance value. Okay, so that is your R1 and R2. So R1 R2, let's provide the data we have the, okay, you could write leave as the as it is, but what we have taken this example from the Hadi Sadat book, so we'll follow this. Okay, this example you could find in the Hadi Sadat. Okay, whatever I am drawing, you could draw and you could see the values. Okay, okay. Now length we are going with this 400, but as they have given small, but we are going for the 400 kilometer. Okay, this filling is being done. Okay, these example what data we are taking, these data are from Hadi Sadar book. You could give, you have taken one, consider one example, and we tried to solve that, and we have to see. Okay, it's also okay, it's same as it is. Fine. So let's run. The errors. Okay, see, in this error is coming now. What error has been coming? You could see initialize command cannot be related cause diagram must contain power queue block. So this is been missing. Okay, you could see these all errors are there, that power queue block is missing. So we'll add a power queue. Okay, power queue is the interface. Okay, you over here you could choose which type. Will select a discrete kind of one power give, and we'll give a minimum value. Okay, let's take, okay, we'll take a minimum value, we'll take a discrete type. Okay, so this is what. Now let's give, now what is being given in this, the voltage source blockade three phase cannot be connected in parallel with the capacitive element defined in the block. Source block or different capacitive element. Okay, so what I have done, I have eliminated the internal resistor. Now click this. Okay, okay, impedance that is been connected, internal impedance that is been not uh, it was not selected, is let's unchecked it. Okay, now I made this fault because to understand, because while solving it's very easy. Okay, you could draw if you know the program, it's very easy to draw if you get the data and all. But the main and the hectic thing, okay, for an individual whenever you do experiment, okay, is your the bugging condition. Okay, if you could bug out the errors, okay, so that will give you the basic. Now I we used to know that without this power GUI, the power GUI, it is your power a graphical interface, okay, which helps to interface whatever data you are giving, okay, whatever the block you are using, okay. So their interface is being required. So this block is very necessary, okay, very essential, because everything whatever is being shown over here is all the coding based, okay. They are being coded, okay, and they have formed in the based on the block, okay, and then this block works, okay. So they need the interface, okay, to know this data, to adapt this data. So that's why this power GUI is very necessary, and that's why I omitted and I have run and I've showed you, okay, that what will be the effect. Now again I have removed this internal. So the error whatever will be shown over there, you could understand from that segment and you could see, okay, you could understand from that particular point and you could answer this out, okay. So this was the entire thing what we could know and we could do about, okay. So let's now run it. Now what we could observe, let's zoom it out a little bit. See, this is your sending end voltage and this is your receiving end voltages, okay. This is what now, as we know about just we have studied, this occurs in your medium and transmission line. In medium you could say, and that's very frequent in transmission line when there is no load conditions and all, okay. That particular segment we have seen. Now let's move ahead with the segment, okay. If what I am going to do is, if I could increase the length again, I'm increasing the length again and again I would be running. See, it is increased, yes or no? Yes, it is increased. Let's decrease this and see what happens. It got decreased, right? From 100 kilometer, okay, this VR is now reduced by that much, okay. Now again we'll go with the 100 part, okay. Let's take 100. See, very less, okay. 110 what we are using and what has been sent over here, right? This is what we are sending, is it right? Okay, if we increase more lower, let's point out as a 50 and 03, okay. So that's the thing, okay, that is the peculiar thing we know about this, okay. For a a layer lower short transmission line, that effect do not come into, okay. That's why. So we were doing with the 400, okay. This is our present rating, okay. That is your 1.226 e to power 05, okay. This is the receiving, and what amount we are sending is this. So if we subtract that, so you would be getting a around 107, okay. or 117. Okay, point 117 into e to the power 5. That much of voltage is being high. Okay, now we'll see the another conditions. Okay, we'll see about under another condition. Okay, that that C is about this. Okay, so what we'll have, we know that this happens when there is open circuited and lightly loaded conditions. Okay, now so what we'll do, we'll apply a load. We have seen what happens in your this open circuited condition. Now we'll add another factor, that is your load. Okay, that will be lightly loaded. Okay, now we'll add a three-phase parallel RC load. Okay, we'll try to add this. Okay, we'll try to this. Three-phase parallel load is being added. Okay, let's see what data we are going to give in this. Okay, now configuration will be Y grounded. Okay, nominal phase to phase voltage, that is will be RMS. Okay, that we have to give. So what voltage we have given? What it was 110 e to power 3. This is what frequency was R50. Okay. And active power was we'll take as 0. Capacitive, there will be no capacitive, we'll take as 0. And inductive power will take some value. Okay, let's take some value. Let's take e to power 6. Okay, this is on load. Okay, we are providing. What we'll get? We'll get only R. Okay, that is your inductive. We will get this. Okay, let's run and see what happens, what changes we get. Okay, see what happens when we apply this inductive shunt inductive thing to this. Your VR is controlled. Okay, this is controlled, right? This is what happens when we do this phenomenon. Okay, okay, so this was what. Now what we have done, we have given a load in this part. Okay, now what this load is being converted into, right? What we told, that we should answer, or we should able to answer that what we are doing. Now we have connected one particular load. Okay, that is your RLC. Now this load is being converted into your shunt reactor. Okay, this has been converted into the shunt reactor, where active power is been given 0, where capacitive power, reactive power is been given 0. Only inductive reactive power is being induced. Okay, let's take 1. Okay, this is what we have done so far, right? We have assumed so far. Now run and see. Okay, now it has been increased. This is 100, 108, and one is 121. Further, if we increase this particular thing, that is your 5. See, there is a digression in this. Again, if you increase this to 6, okay, and run. Let's run for 1 minute. See, another there is a digression. If we make this as 10, again there is a digression in this. Okay, so how much you boost up, it will be like, let's see, if we are using 3 phase and it is showing only one segment. Okay, so we'll write RMS. Okay, one error has been occurred. Okay, we'll see, just a minute, we'll see about this. Let's then stop. Okay, now fault is been covered. Okay, and the fault is, let's run. Okay, now that was your error, RMS. Okay, now this shows the perfect thing. Okay, Okay, now I will discuss what the error it was happening. Okay, what we have taken the this RMS value, and it was 60 and 120 initial RMS value that I have changed to the what we have used. Okay, we have used 50. That's why the error was there. Okay, because this error, the other segment. Okay, let's see. I will show you first. So these things that you have to very keep in mind. See, it will be a okay. The all the three phases have a different rating and different rated values. Okay, so this is what you have to keep in mind while doing this experiment. Okay, the experiment requires very keen thing to know. Okay, else you will get a error. Okay, the error is very frequent. The error will be coming into your action. Okay, the error will be there. Okay, will also decrease to this to the initial value that it was. Okay, that is e to power 5. Okay, and we'll change this to as 50. Okay, this is 50 and we'll run. Now see, this is the perfect thing what we were doing. Okay, this is our voltage what we are providing to the from sending end to this transmission line. Okay, this transmission line is of 400. We'll reduce this 400 to 300 and we'll see what will be the effect to it. Okay, it will be your lesser than. Why it is being lesser? Because this over here we are using a 10 kilowatt. If we reduce to 1 kilowatt, let's see the effect. Okay, this is 1.159. Now if we reduce this segment, if we make as an open circuit, we could see the values. Okay, 117. If we go with the original part, that was your 400. Okay, and we run to this is your 1.109 e to power 5 for all the phases, and this is what we are getting at the receiving end. So this is the difference. So this is the fraternity effect or Ferranti effect. Okay, this is the Ferranti effect where receiving end voltage is being okay. Either you could reduce the size if you do not want to reduce the size, because generally this do not happen in short transmission line, it happens in longer transmission or medium transmission lines. So what we do, we add a shunt reactor to it in parallel. Okay, so what we are doing, we are adding, we don't have an shunt reactor right now. It will again create a complex to create, and we have to write. So what, instead of that, what we are doing, we are adding a parallel RLC load to the receiving end, okay, at this particular end, and that is being converted into the reactor. Shunt reactor means it is a reactor which is connected in the parallel. It is not connected in series, it is connected in the parallel. Okay, shunt reactor is connected in the parallel. So what data we have to give? 110. This is 50. There is no active power in this, and there will be no capacitive reactive power in this. Only inductive power has been given. Okay, and we'll see. Let's add to this, and you could observe, you could see by adding this, you could reduce this segment. Okay, now it is been reduced. Okay, it was earlier 1.26 and it is reduced. Now further again, if you increase this to 5, there would be another decrement in this particular. It will be keep constant, it will be degradable. Now another again, if we increase this to 6, there will be again a degradation. Okay, 120. And again, if we degrade to this, let's use 10 E run. Okay, see, it is being degraded. So this is how it works. Okay, this is how you could this observation is your, okay, what we have seen in this MATLAB, that how to reduce that, how to, what is a Ferranti effect, how it can be reduced, what is the answer, okay, if it is there for open circuited and lightly loaded condition, and what is the scenario when the transmission line is short more and that. Okay, now, so what is being asked, what I told, there is a question that need to be answered. Okay, now that question was for 200 meter, what will be the, okay, 200, what will be the receiving end voltage? So I have removed this part. Okay, for 200 we could say that it is 1.131 into per 5 at the receiving end, and the sending end is 10.4 into power 5. Okay, this is what we could say in an open condition. Okay, this is the factor. This is was asked. Okay, in that theory it was written what will be the means post lab questions to be answered. Okay, so this is the answer what you get, right? So these data you have to take, you have to design, okay, and you could write, and you could write the every explanation, right? Okay, fine. So let's go with the another segment that we were discussing. We'll close this part, we'll close this part, and we'll start with this. Okay, now what we'll use the another very important segment of MATLAB, that is your coding. We'll use the MATLAB program to simulate this Ferranti effect. Okay, so the aim is to find Ferranti effect of a 5,000 kilometer transmission line. Okay, and to plot locus of voltage for the given problem and verify result in MATLAB. Again, this is what you have to verify. Okay, so the problem is a three-phase Hertz transmission line of 5,000 kilometers long. Okay, the line parameters are R is been given 0.125 ohm. Okay, X is given your 0.4 ohm. Okay, and Y is given, that is your 2.8 10 to the power minus 6 mho per kilometer. This data is being given to us. Okay, now thing is, if the line is open circuited with a receiving end voltage of 220 kV. Okay, find the RMS value and phase angle of the following. Use receiving end line to neutral voltage as a reference. Okay, you have to find using this, means this is a question that is being given and you have to find. Okay, now what reference we have to take? Okay, first the incident and reflected voltage to neutral at the receiving end. The incident and reflected voltage to neutral at 200 km from the receiving end, and the resultant voltage at 200 km from receiving end. These factors we have to see. So first we'll see. Okay, now the same thing you have to solve. Okay, that same thing you have to solve, and then you have to find. Now how you could find? Okay, what data has been given? You're receiving and given line parameters, every data is been given. So what is been left? Okay, what data is been not given? Okay, what we have to find? We have to find the sending end voltage. Okay, VR is given, IR is given, Z is given, everything data has been given. Okay, now we'll use this data for writing a code, and we'll see. Okay, and we'll observe this phenomenon to happen. Okay, we'll draw and we'll write and we'll see all the segment. Okay, whatever is happening and whatever we have to do. Okay, now in this equation, okay, this equation would be used. Okay, this equation will use in the coding segment. Okay, now so where Vs is your sending end voltage, Vr is your receiving end voltage, IR is your receiving end current, Zc is your surge impedance, and this alpha and beta Okay, this alpha and beta are the attenuation constant and beta is a phase constant. So these values are will given. It will be given. Okay, this will take this value as 0.1683. Okay, and this beta value as 1.683. Okay, this value will take. Okay, this two value will be taken. Okay, now is as a phase constant and x is the distance. Okay, where x will use coding in this as a L because x would be used somewhere. Okay, so we'll over here x it has been given, but we'll use L because your L is already be in x would be using denoting some of the factor. Okay, now so it is been noted that the first half of the right side of the equation 1, okay, this first half is also known as incident voltage, which keep increasing with length of the line, and the second half is known as a reflected voltage, with decreasing the length of the line. Okay, this segment you have to keep in mind. Okay, one would be increasing, so our motto is to draw to find, okay, and to find the location, okay, of for the voltage and for the phase. Okay, so how will phase the imaginary and part we'll see using that to segment. Okay, so let's go to your MATLAB. Okay, in this you could use this script writing or live script writing. So we'll go with the live script part. Okay, so what happens in live script part? Okay, whenever you are writing any segment, okay, so it will be directly run. Okay, you do not require to run. We'll save that in a line and we'll write. Okay, so first what we'll do is we'll write the situation that what it effect. Okay, so there is one particular symbol called this. Okay, this it's used to write uh, commands. Okay, the comments. Okay, you could comments. Okay, program to illustrate the guarantee effect. Okay, program to illustrate the guarantee effect. Okay, next what is will be the it simulates. Okay, it simulates. What is simulates? It simulates uh, the effect. Okay, it simulates the effect by varying the length of the line. Okay, will vary. Will we have 5,000 kilowatts? So will kilometers. So will with the 10 factor will increase and will start. Okay, so it will be from 0. Okay, that is your N2 to 5,000 kilometer in steps of 10 kilometer. Okay, this will understand and will write, and will also will plot. Okay, plot the sending end voltage. Okay, sending end voltages and phasor. Okay, we'll write. So we'll start writing the codes. So write first is your CLC, then it will be clear all. Okay, then we'll take a VR value that is been given, that is equals to 220 uh, 220 kilowatt. Okay, so 220 kilowatts, we'll have to write e to power 3. Okay, 220 e to power 3, and it should be in RMS, so we'll write SQRT 3, right? Perfect. This is your one code. Then what we have to give, we have to give alpha value. Okay, so alpha value, what we have taken, we have taken 0.163 e to power minus 3. Okay, then there is a beta is given 1.0683 e to power minus 3. Okay, this we have taken, alpha beta value have taken. Okay, what else it was given? Length. Okay, L, that is your 5,000. Okay, that is your L is your 5,000, and right now, so we have to increment, we have to check the voltage from this your 0 to 500, right? Now when you are going to increase this, so first of all let's write the equation. Okay, so Vs, so Vs would equal to your VR by 2 into exponential, okay, alpha, yeah, alpha, exponential alpha, and what was called alpha into I. Let me see once. Okay, alpha into I. Okay, now into beta exponential j into beta into I. Okay, okay, this is the first half, plus this will be your copy, this will be paste, and this is your second half. Okay, so in second half there is a small change, that will be your alpha part. Okay, this would be your minus alpha. Okay, and there will be your minus of beta. Okay, now this has been done. Now you have to take a loop, so we'll write a for I equals not equals to colon 10. Okay, means this will be taking 2 step, 10 step will take as L, not small l, the capital L. Okay, this is how you could write, or we could take I equals to 0, I equals to 0 colon, right? Now this would be ending, right? Now So this has been done. This is all okay. Now we have to take the value. Value means we'll write your x, okay, that would be equal to, now it is a loop, so it will increase from 10, so we'll assume a value. We'll take a, let's take a k. So for if you're writing k, so you have to give that universal value that k equals to 1. That initial factor should be announced. Now if we'll take x as a real value of this entire, okay, all the real values will be solved, so it will take as a real, we'll get the vs, okay. Then we'll take y as the imaginary part, okay. We'll write equals to img vs, okay. This has been done. Now what we have to find, okay, this data has been saved in this particular format. Now when k is 1, now it should be integrated. If we are saving k over here, so that should be integrated. So we'll write k equals to k plus 1, okay. Otherwise it will not save the value, it will save the initial value only, okay. When the loop would be, first loop would be running, that value would be saved. Now you have to save the entire value till the k value is being there, so that we are increasing, okay. Whenever the, till what loop is will go, that value would also go, okay. So that would be k equals to k plus 1, that will be increment, okay. Now this has been done. Now what is your to define, okay, to define the, to plot the graph, okay, we'll take another two value, means that is will be, will take a vs value. Vs would be saved in one particular format, so we'll save the vs value in one. So what will be the vs value? Let's take one, okay, will p will k, and that is your equals to vs. So this value is saved in this. We'll take q would be equals to your I, the number of rotation, okay, that is your length, means at what particular length what is the voltage. So we are accounting that two value, okay. We'll plot amongst that two, okay. Now, so this loop task is being done. Now when loop task is being done, what you have to do, you have to bring out the figure, you have to draw the figure. Let's give figure 1. So what will be your figure 1? Figure 1 would be your plot q comma q. Okay, that voltage versus line length, okay. This will be down over here. Figure 2 will be plot your x, y. Okay, means you have to plot your phase, okay. is what is the okay, so let's see the value. Just run it. Just run it. Okay. Now it has been fixed. Now I can run this particular part. It was written in the spelling of clear was wrong. Okay, see these two images being formed. Okay, so what else? Let me draw, let me copy this. Okay, let's copy this into script, paste. Let's run our system. Path. Let me see the VS value. Okay, this is your VS value. Okay, this is your VS value. Fine. See over here, you could get. Okay, this is your warning at line 22. Yeah, it's okay now. Okay, so you could see from this part. See, we'll see. First of all is The Vs value is 1.009 to power 7, okay, e to power 05. This is the magnitude, and see over here it is 220 e to power 3 root 3. This is the value, okay, this is the difference, okay, this is the difference because line length is 5000 and it is a condition in the open segment, okay, this short circuit, and this is the open part. When this is open, this is why it is being happening, okay, why this is the Vs, okay, sending end voltage is this and receiving end voltage is this, okay. We'll also write the VR value, okay, that is your VR. Now we'll see the values, see the difference, okay. Sending end voltage is this and receiving end voltage is this, okay. That's the difference, that's the Fonity effect, okay. It's a 5000 kilometer long line, okay, and we are giving this much of current, and this is what we are getting, okay. Now, okay, see the values, okay. What it is being, that P means what is the value of Vs at every 10 kilowatt or the kilometer distance, okay. This is what I am able to show you, okay. To start from 1 to the 500 times, okay. This is the final value what we are getting, that is your 1.00970.9. So it is been running, the loop is been running for 502 times, okay, for the 10 kilometers. First is your 0000, then 1.127.00 I. So this is the increment, okay. It is being done by the increment of 10 kilo meter, okay. So every one loop will boost, means first loop ends, so it will be for 10 kilometers, and another loop ends, but then it will be 20 and 30 40 till 5000. So these are the Vs value, okay. This is the Vs value for the entire segment, okay. This is what we could easily show you, and this figure, okay, this is the figure you could see. This is your, this is your increase in length, okay, at 500 kilometer, 1050, 5000 kilometer, and this is your voltages, okay. See how it is been increased, okay. So it will be 0 0, then over here it is 1, then it is been increment, and this is the entire flow of this, okay. And this is your figure, okay. This is your entire figure of your phasor, okay. This is how your phasor look like. So it is the very exponentially, okay. The increment is exponentially, Okay, now so this figure, okay, this figure, from this figure we could observe, okay, from this particular figure we can observe that as the line length increases, okay, the incident voltage wave increases exponentially. Okay, as the line of the conductor increases, it is increasing exponentially. Okay, we could see from this figure. See, as the length of the conductor increases, okay, line of the conductor, voltage also increases exponentially. Okay, it's increasing exponentially. Okay, so it is observed from this entire, these two figure, or from this figure, that the line length increases, the incident voltage waveform increases exponentially. Okay, while the reflected voltage, okay, wave decreases. Okay, whereas voltage wave is deprecated. Let's go to the, okay, where the reflected part gets decreases. Right now, so this figure, okay, this figure, okay, this figure apparently say it is apparent from geometry of this figure. It's a geometry of this figure, okay, that the resultant phasor, okay, this is a phasor figure, okay, that the phasor we have to draw, because we, for drawing this, we have taken your imaginary and real part, okay, of Vs, okay, Vs of Vs, positive and negative part, we have taken this. Okay, the first half and second half we have taken in this particular figure. Okay, so it is very apparent to say for this geometry, by seeing this geometry of the figure, that the resultant phasor, okay, the resultant phasor, that is your Vs, okay, the resultant phasor voltage, that is your Vs, is such that Vr, okay, your Vr would be more than your Vs. From this you could say that Vr would be more than your Vs. Okay. Yeah, you could say that this is your Vs and this is your Vr. You could say the Vr would be more than your Vs. Okay. Fine. So this was the experiment that I wanted to uh, get in with you now. So we have seen uh, Ferranti effect. Okay, the experiment we have seen in MATLAB, we have seen in uh, in 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 coding. Okay, we have gone through uh, gone through with the both the methodology and both the way to solve this. Okay, I have utilized your MATLAB part. I was hoping to do with the help of your virtual lab, but certainly virtual lab is not functioning. We'll see once. We'll see once if it is working. We will be looking into that, or else we'll go with the. We'll end this thing. Okay. Uh, no, so it's not opening. Okay. So we could finally end your this paternity effect. Okay, we have seen in both the ways. Okay, we have coded that, we have simulated that. Okay, so we have seen both the methods. Okay, so you could easily go with this particular segment. Okay, now So this was all about the two experiment, that is the only one experiment, that is Ferranti effect. Sorry, Ferranti effect. Okay, it's a Ferranti effect. Okay, we'll look forward with more upcoming labs. Will come with different segment in MATLAB, how we could draw, how we could install, okay, and how to draw a lot of things. Okay, we'll go into this particular segment. Okay. Okay, so we could thank you for being, so I could end this segment